So 7.1 and 7.2 in your book are what talk about inverse functions. 7.3 is what I need to start today. I doubt I'll be able to finish it. Let's get you started before spring break comes, and then we'll review and finish it up after spring break. You'll notice if you look at any of my notes that there's kind of a break. I upgraded half of my notes and I didn't upgrade the other half of my notes. So on the website it's all in the right order, okay? But I never upgraded these notes, so you're just going to have to deal with black and white. What I want to do for trig equations, the way I like to present this is kind of break it down into the 4 basic types of trig equations that you're going to be expected to know how to solve. So a trig equation, what we want to be able to do is solve things like sine of theta equals 1/2, which is probably the most basic trig equation you can ever see in your life. Okay? Or something like 2 sine of theta minus 1 equals, I don't know, maybe 2. We want to be able to see if we can figure out what theta is. Or we can put squares in there. And we can mix some tangents in. Maybe sine theta times tan theta equals 0. So we want to be able to solve different types of trig equations. And there's kind of 4 categories that these break down into. I'll just be able to tell you what the categories are and go through the first one, and then we'll leave the other ones for next. So there's trig equation, there's linear trig equations. These are the easiest. Linear trig equations have an exponent of 1 on the trig function. So for example, something like 2 sine theta plus 1 equals 0. This is a linear trig equation because it has a 1 signed to the first. The strategy for solving this is going to be to isolate the trig function just like you would any other equation, right? Like subtract 1 divided by 2. All right, so treat this whole sine theta like a variable. This thing is like x. All right, so this equation is kind of like 2x plus 1 equals 0. You solve for x first, and then once you know what x equals, you can go to your unit circle and figure out what theta equals. So those are linear trig functions, or trig equations. There's trig equations of multiple angles. So what I mean with this, you're still going to have the first power on your trig function. You're not going to have any squares or cubes or anything funky. But instead of having just a theta inside, you might have a 2 theta, or a 5 theta, or 3 theta. And when there's a number multiplying the angle inside, that changes the strategy you need to use to solve it. So this multiple angle means there's a number multiplying your angle. Then you have quadratic trig equations. What do you think that means? Quadratic. Squared trig function. Right? Quadratic equations have squares in them. So something like 4 sine squared theta plus 3 equals 0. This is a quadratic trig. And again, kind of like the linear trig equations, you're going to treat this like a squared variable. And you first solve for the variable, you first solve for this x here, then you can use that result to get theta. Going back to the unit circle. Then there's the other category. So basically anything that doesn't fit into any of these, I call other. And what this comes down to, there's kind of two types you're going to see here. There's equations where you're going to have to use one of your fundamental identities to try and solve. So something like cos squared theta plus sine theta equals 0. Right? Because this has two different trig functions, you're going to have to rewrite cos squared first before you can solve this. But we have an identity we can use to rewrite cos squared, so this is okay. So that's one thing to look for here. And then also factored or equations that use the zero product principle. Factored equations. Like if I give you sine theta times cos theta equals 0, you can solve that. Do you know how you would solve that? Or how you might start to break that down? So when you have a product equals 0, do you remember the trick? Set each factor to 0. If a product is equal to 0, you can set each one to 0. Sine theta equals 0, cos theta. So these are the different types that you're looking for. It's easy to identify linear because it has only a trig equation to the first power. Nothing else. It's easy to identify trig equations with multiple angles because they have a number in front of theta. It's pretty easy to identify quadratic because they have just a squared trig function. The other ones are the tricky ones. Okay, the other ones are where you have to somehow use a previous fact to simplify it. Okay, so we'll talk about those. But let's just go through linear today, and then I'll pick up with the rest after spring. I have to talk to you about domains. So before I get to my examples, and this is kind of important, this is going to cost you points. You have to read the instructions on these problems. You have to. I know. The instructions are going to be of one of two forms. It's either going to say find all solutions, or it's going to say solve, or something like solve on the interval 0 to 2 pi. So for example, say I want you to solve for me the equation sine of x equals 1. Sine of x equals 1. So one way you could do this is say, all right, well, in order for sine to equal 1, I can go to my unit circle, and I can say, where is my y value 1? Right, this is your y value. Sine of x, this represents your y value. And I want to know on the unit circle, where is my y value 1? Where is it 1? Right here. It's not 1 down here, right, because this is negative 1. And it's not 1 over here because these are 0 for the y value. So this is the only angle where sine is equal to 1. Okay, that was a lie. This is not the only angle. Why not? Every time you revolve by a full revolution, you get the same place, so you have the same sine value. So if I say find all solutions, then not only do I want pi over 2, but I want to know also that if you rotate a full revolution, 2 pi, that's another solution. Or if you rotate 2 full revolutions, that's another solution. Or if you rotate back a revolution, that's another solution. So all solutions here would be x equals pi over 2 plus, we write it as 2 pi times n. So when you see all solutions, you add this extra counter, right, where this keeps track of how many revolutions you've gone. So n counts the number of revolutions. If n is 1, you've gone 1 extra revolution. If n is 2, you've gone 2 extra revolutions. So whenever you're supposed to find all solutions, you have to add this extra term that counts revolutions. And the n is, like I said, it's just any integer. It counts whether you've gone 1, 2, 3, 4, 5 extra revolutions or not. Now, if it just says solve on 0 to 2 pi, what does that change? What do you think the answer is over here?
Pi over 1.
Just pi over 2. Right? The only place that sine is equal to 1 between 0 and 2 pi, this is the only angle. If I go a full revolution past this, I'll be bigger than 2 pi. And if I go a full revolution backward, I'll be less than 0. So if you're stuck between 0 and 2 pi, your only answer for this is pi over 2. These are no good. These extra revolutions can't happen. They're between 0 and 2. So be careful. If I want you to find all solutions, I want this extra 2 pi n factor. If I want you to find just solutions on 0 to 2 pi, I want pi over 2. That's just no extra revolution factor. So this, there we go. Find all solutions. Right, that's what it says. Find all solutions to each equation. Start. These are linear, okay? This example, all the trig equations are linear trig equations. And I can start you off with probably, simple as we can get it. Cos x equals 1/2. I want to know what x can be. Usually, if I give you something like this, where there's trig functions on both sides and extra numbers. You want to move things around so that your trig function is isolated. But if I give you something simple like this, the trig function's already isolated and you can turn straight to your unit circle. Right? This is just asking you to look at your unit circle and figure out where cosine, which is your x value on the unit circle, is 1/2.
Pi over 3.
Yeah. Right. Up at pi over 3, you will be at 1/2 root 3 over 2, so that works. Is that the only angle? No. What else? In the fourth quadrant, cosine's positive again. What angle would this be? Negative pi over 3 or 5 pi over 3. So since I asked you to find all solutions, what would you write for your answer? Would you write pi over 3, comma 5 pi over 3?
No. Pi over 3 plus 2 pi.
Right, this is only the two solutions between 0 and 2 pi. This is no good for these instructions. I want pi over 3 plus 2 pi times n, so any number of revolutions. And 5 pi over 3 plus 2 pi n, any number of revolutions. These are your two. These are your two formulas for what x can be.
Do you want both of them or just?
You need both of them. Because this one, if you just put this one, then you will get all the possible ways you can land here,
I see.
but you won't get any of those. Let me do this. Again, we're trying to find all solutions. 5 sine theta plus 1 equals 3 sine theta. In this case, the trig function is not isolated, so what do you think happens? You got to move things. You got to do some algebra. So I want all of my variable terms on the same side and everything that doesn't have a variable on the other side. So I'm going to treat this kind of like an x and just subtract it over the other side. But I have to subtract the whole term.
Is it okay if I look the other way?
Yeah. Shouldn't matter. But then this 1 doesn't have a variable in it, so I'm going to move it to the other side. So I got rid of these. I got rid of these. And what do I have left? Yeah, 5 sine thetas minus 3 sine thetas gives me 2 sine thetas, collect like terms, equals -1. This 2 is connected by multiplication since it's outside, divided over. Now you have an isolated trig function equals a number. Turn to your unit circle. You guys all have this memorized, or hopefully close to memorized. Sine is negative, let's see. Third and fourth, -1/2 for sine, down here and down here. So what are these angles? Huh?
Negative pi over 3.
Whoa, 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 whoa. So in the first quadrant,
Pi over 6.
in the first quadrant, the 1/2 for sine happens at pi over 6, right? So over here, this -1/2 is going to have a pi over 6 reference angle. So this is 6 pi over 6 7 pi over 6.
Is that 11 pi?
Yeah, if you go all the way around, it's 12 pi over 6, so this would be 11 pi over 6. So how would you write all solutions to this equation?
7 pi over 6.
Yes. 7 pi over 6 plus any number of revolutions, or 11 pi over 6 plus any number of revolutions. That's all solutions.
Would, make a listing of the negatives if you're going the other way?
So the negatives are taken into consideration by this formula because n can be any integer.
Oh,
N can be positive or negative. So like if I plug in -1, that gives me the other way.